recording. Okay, thanks for the reminder. Okay, so let me say the things that I said before the recording again, just in case people want to watch this recording later on. So in the last session, we talked about termination analysis. We saw that the problem of termination analysis is undecidable, and then we looked into the special case where we were given a linear program and we wanted to synthesize a linear ranking function. And by linear, I mean that the ranking function was a linear expression based on program variables at every line of the program. And what we saw was that we really depended on invariance. We assumed that we have invariance at every line of code. And now in this session, we're going to really talk about how we can get those invariants. So the problem that we are interested in is invariant generation. And the techniques that we're going to see are actually very similar to the techniques that we saw for termination analysis and for synthesis of ranking functions. The main difference is that here we are synthesizing invariants. And then you will see that the complexity is actually also much higher. So if you recall from the previous session, what we did with linear ranking functions was that we wrote the constraints that had to be satisfied by a ranking function, and then we applied Farkas lemma to these constraints, and this gave us a linear programming instance. And then it's very well known that linear programming can be solved in polynomial time. So in general, the problem that we had to solve in the previous session could be solved in polynomial time. But the problem that we have in this session, which is how to get those invariants, is actually going to turn out to be much harder. So it's easy to show that even in the linear case, so assuming that the program is linear and the invariants that we want to generate are linear and so on, this problem is still NP hard. But that's not really what I'm going to discuss in this session. In this session, I'm going to discuss this paper, which basically just gives an algorithm. And this is actually one of the most classical papers in this field, in field of invariant generation. And the main reason that this is classical is because it was pretty much the very first invariant generation method that actually gave us completeness guarantees. So again, just to remind you from the previous session, we had three different notions. We had soundness, completeness, and termination. So the idea behind soundness was that, well, in case of termination analysis, if my algorithm says the program terminates, it should really terminate. The idea of completeness was that if the program terminates or has the desired property, then my algorithm should figure that out. And termination was that, well, my analysis algorithm or my verification algorithm should itself terminate. It shouldn't run forever. Now, if we want to formulate the same properties for invariant generation, we're going to have to do a little bit more work. And I'll get to that. But for now, what we want to do is basically have a very informal idea of what we mean when we say that an invariant generation method is sound or complete. So when is an invariant generation method sound? It's sound if every invariant that it generates is the correct invariant. So if every invariant that is generated by our approach actually holds in the program, then our approach is sound. But when is it complete? It's complete if it can find every invariant. Okay? So suppose that I tell you, instead of just asking you to give me some linear invariant, I tell you, okay, give me a linear invariant that proves a specific inequality at some point in the program. And the idea is that if such an invariant exists, then the approach should be able to find it. And if the approach can always find these invariants, then it's called complete. Okay. So let's get into this paper. What I'm going to do in this session is pretty much just follow the paper and explain to you the ideas in there. And if we have time, then I'm going to also switch to this other paper, which is actually something that I was a co-author in, and extends these ideas to the polynomial case and also to non-deterministic and recursive programs. But we'll see if we will have time or not. Okay. So let's start with the very basics. So let's start with defining what an invariant is. Let me make sure I can see the chat. Okay. So an invariant is basically an assertion somewhere at some point of the program or at some line of the program, such that whenever the program reaches that line, this assertion holds. And this is a very general definition, so we're not assuming anything about the assertion. Okay. So for example, I can show you a program here. So consider this very simple program. And we have a precondition. So at the beginning of the program, we are assuming that this condition holds. And then we are generating some invariants. So if at the beginning of the program, I know that 100 minus y squared is greater than or equal to 0, then of course in here, I know the same thing as well. So this is the same as this. So I have this invariant at this line of code. And this holds in every run of the program, right? And also here, I can also have the same invariant. Sorry, so here it's because the else part is being run. So as an invariant, I can have the negation of the if condition. And so this whole idea of invariant generation is quite similar to what we were doing with Hoare logic. So a post condition is a very special case of an invariant, right? So you assume the precondition, and then the post condition is basically an invariant that holds at the end of the program. So that's easy. And what we're going to do is we're going to see how we can generate these invariants. So the idea is, for example, suppose that you want to prove a Hoare triple. So you're given a program, you're given a precondition, and you're given a post condition, and you want to prove it. So one way of proving it is like the homework that you had, you can write a proof tree. But another way of doing it is to actually find the invariants or inductive invariants, and I'm going to get into that at every line of the program. So one use case is this. So you have a Hoare triple and you want to prove the Hoare triple. Another use case that we have already seen is for generating ranking functions and proving termination of the program. But there are many more analyses that depend on invariants. Basically, anything that you see in static program analysis, almost all of the analysis assume that some sort of invariant is given as part of the input. So in a sense, invariant generation is probably the most important problem in all of program analysis. Okay. So this was the definition of an invariant. So an invariant is basically an assertion that holds at that point of the program whenever the program reaches there. But then we also have another definition, and this is the definition of an inductive assertion. So the idea of an inductive assertion is that you can prove that this assertion always holds using induction, and that's why it's called inductive. So we say that an assertion is inductive at some program location or at some program line if the first time that the program gets to that location, this assertion holds, and then any cycle in the program that starts from this location, goes and visits somewhere else and comes back to this location, also keeps the assertion intact. So the assertion should hold the first time we get to this location, and we also know that every cycle keeps the assertion. So we can prove by induction that the assertion always holds. So if we have an assertion that is inductive, then of course that assertion is also an invariant. And normally, instead of just saying inductive assertions, we just say inductive invariants, because That's what they are. Okay. And there are many different ways of generating inductive invariants, but the main contribution of this paper is that it gives completeness guarantees. So I'm going to skip over the previous works here, and I'm going to just get into the definitions and the formal stuff. Okay. So first of all, in this work, they basically model a program as a transition system. So what is a transition system? A transition system is a tuple, P, which consists of these parts, V, L, L0, theta, and T. So V is a set of variables. These are program variables. So for example, in this program, we have X and Y. So V would be X and Y. L is a set of locations. And the way that we think about this is that L is basically the set of lines in our program. So we have, for example, line 1, line 2, line 3, so on, and L is the set of lines. There is an initial location or initial line, L0. There is a precondition or an initial assertion, theta. So, for example, here, this is our precondition, 100 minus y squared greater than or equal to 0. And this is something that we assume always holds at the beginning of the program. And then we, of course, have a set of transitions. And the idea here is that the transitions in our transition system basically encode all the semantics of the program. So each transition itself is a tuple. So it has a start location or a pre-location L, an end location or post location L prime. So for example, here, if I'm at this point, if this if is my L, then I have two different transitions. I have one transition inside the then part to here, and another transition to the else part, to the skip, right? And then every transition also has something that is called a transition relation. And in this case, the notation is rho of tau. So tau is the transition, and the relation of this transition is rho of tau. And what is this relation? Well, it basically encodes two things. It encodes the condition that should be satisfied in order to take this transition, and also the updates that happen to the variables. So for example, if I want to transition from this if into the then part, then I know that this condition should hold. X squared minus 100 should be greater than or equal to 0, right? And if I want to go, for example, from this line where I'm assigning y to x to the next line, which is the end of the program, then I know that some update should happen, right? And basically, the idea here is that this transition relation encodes both of these. So how does it encode both? I'm going to write it in the chat. So consider our set of variables, which is x and y. So it creates another set, which is what we call the primed set or the post set, v prime, which consists of the primed versions of these variables, x prime and y prime. And so the idea is that we are distinguishing between our variables before this transition and after this transition. So before the transition, we call the variables x, y. After the transition, they become x prime, y prime. Okay? And so let's say that I have the transition tau, which is from this if here to the then part, right? Then what should I have? Well, in order for this transition to take place, I should definitely have x squared minus 100 greater than or equal to 0. So this is my transition relation for going from the if here to the then part, okay? But now consider the transition from this line here, x, which is assigning y to x to the end of the program. What would my transition relation be there? Well, I don't have any conditions anymore, but I have an update. But I can write that update as a condition too. So I can write it like this. So this basically means that x prime equals to y, means that after the transition is done, the new value of x is equal to the value of y before this transition was done. Okay? And of course, we can have some dummy equalities as well. So because, for example, y is not touched, we will have y prime equal to y as well. And generally, we add as many of these equations as we can. Okay, so basically the transition relation is now just a bunch of assertions over v union v prime. So over the previous values of our variables and the new values of our variables. Okay, so yeah, as it says, v prime represents the next state variables. Okay, and so it's also assuming that we have n variables, which are called x1 to xn. And we do this priming with all sorts of expressions. So if you have an assertion and you put prime, this basically means that just prime all the variables in this assertion. Okay. Now, what is a control flow graph? Well, if you have a transition system, which is basically your program, then the control flow graph is the graph that shows all the possible transitions. And every label or every line of the program is a vertex in the control flow graph. And there is an edge between two vertices, a directed edge, if there is a transition from this line to that line. So the control flow graph is pretty much the same as the transition system, except that it's ignoring all these transition relations. Okay. And then we can, of course, define a path in this control flow graph. And so if you have a relation, for example, this row of tau, which was the relation that's that corresponded to the transition tau, you can basically put these relations together and just compose them, and you will get a similar relation for a path. So if you have a path P in your transition system, you can get a relation rho of P, which is basically the composition of all those relations that you had before. So what does this mean? This means that, well, a relation for a transition basically told us what conditions should be satisfied in order for us to be able to take that transition, and also how the variables are updated, right? So now if I have two transitions coming right after each other, if I have a path, I can also compute what condition should be satisfied in order for me to be able to take that path. And I can also compute what updates happen in that path. And this is just the composition of the relationships for the transitions in that path. So the extension from the relationship of a transition to the relationship of a path is very straightforward. Okay, so we now have this notion of rho of P. Another important notion that this paper really depends on is what we call a cut set. So let me give you the intuition before giving you the formal definition of a cut set. So we want to basically find an inductive invariant. And we said that an inductive invariant is an assertion that holds the first time we get to some point of our control flow graph, and also holds every time we take a cycle from this point back to itself, right? So the idea is that we want to somehow get rid of these cycles and just choose some points of our control flow graph such that we can find an inductive invariant at those points. And then we can just compute the inductive invariant at other points based on the invariance that we have at those points. And this is why we use a cut set. So a cut set C of our transition system P is basically just a subset of the locations, so a subset of the lines, such that it satisfies this property. Every cycle, every cyclic path in our transition system should go through at least one of the vertices or one of the locations in our cut set. So a set C is a cut set if every cycle has to visit C. Okay? And if some line or location is inside our cut set, we call it a cut point. Now, what does this mean? This means that, well, if I have invariance at every cut point, then I can compute invariance at every other point of my program as well, right? Because basically, I can start from a cut point and go ahead to some other point, and the invariant at that point would just be the invariant that I had at my cut point, composed with the relationship of the paths that I went through. Okay? But to make life easier, we can just assume that our cut set is the set of all lines in our program. So if you don't want to just generate invariance at some points, you can just generate invariance at every point. So we can assume that C is just the set L of all lines in our program. And then a basic path is a path between two cut points. And again, if we take our cut set to be our entire program, then a basic path would be any transition. Okay? So based on this, now we can actually formalize the notion of our inductive invariant or inductive assertion map. So let's say that as input, we are given a program P, and we are also given a cut set C of P. Again, you can just assume that C is the set of all lines in the program. Okay. So an assertion, let's say that we have an assertion eta of C, eta C of L for every cut point L. So eta C is just an assertion for every cut point. So at every line that was in my cut point, or if my cut point is the whole program, at every line of the program, I'm given some assertion which I'm showing with eta C. Okay. We say that this whole thing, this set of assertions, this eta C, is an inductive assertion map if it has two if it satisfies two main conditions and has two properties. And these properties are basically what we use in induction. So the first property is initiation, which is very similar to the base case in induction. And it says that for every basic path that starts at the beginning of the program, starts at line L0, and goes to one of these lines in my cut set, I should have this. And what does this mean? This is basically saying that if my precondition theta holds, and if I respect the relationship of this path, because the relationship of this path gives me some constraints on how, on what should be satisfied in order for me to go through this path. If I satisfy both of these, then when I get at line L, I should satisfy the condition eta. And the prime here is, of course, because after getting to the line L, I have the primed version of my variables, right? So the initiation condition is basically this, that for every basic path that goes from L0 to L, if theta and rho of that path, the relationship of that path are satisfied, then when we get at L, eta should also be satisfied, okay? Now, what is consecution? Consecution is just saying that, okay, if I start from some line L, in my cut set and go to some other line L prime in my cut set. Then what happens? Well, this is like the induction step in normal mathematical induction. So at line L, I knew that eta of L used to hold. And I also know that I've gone through a path P, so I should respect the rules of the path, and I should satisfy the relation rho P. And if this is the case, then when I get to the next location, when I get to location L prime, then at that point I should satisfy the invariant or the eta at L prime. Okay, so basically if eta holds at L, and if the path relation holds, then when I get to L prime, and now I have another prime here because my variables are probably updated, then when I get to L prime, I should satisfy eta at L prime. Okay? So this is nothing but just mathematical induction. And that's all. So if you have an inductive assertion map like this, so if you have some eta that satisfies both initiation and consecution, of course you can show by mathematical induction that this is definitely an invariant. Okay. So now the situation is very similar to what we had in the previous session for generating ranking functions. So the idea here is that, again, we have a bunch of constraints on a function. So previously our function was our ranking function f. Now our function is basically this eta here. And we want to somehow synthesize this eta, this function, such that these conditions hold. Now, again, just like the previous session, the problem is undecidable. And it's actually undecidable according to a theorem which is due to Rice. So if you look at Rice's theorem, it basically says that every non-trivial semantic property of programs is undecidable, and this is a non-trivial semantic property. So just like the previous session, the question that comes to mind is which cases are not undecidable? And just like previous session, we're going to look into the linear cases. So what happens if my transition system is linear? So this was my transition system. Let's say that it's linear. What do I mean when I say it's linear? Well, I mean that the constraints in theta, which was my precondition, should be linear. And also, whenever I have a transition, the transition relation rho of tau should only contain linear constraints. Okay? And let's say that I also want to generate linear inductive assertion maps or linear inductive invariants. What do I mean when I say my inductive invariant is linear? I mean the function eta is linear at every line of code. Okay? So, yes, I'm going to skip over these because the definition of linear and so on is obvious. There's also an example in the program of how you can, in the paper of how you can take a program and turn it into a transition system. But I think that's also obvious, so I'm not going to do a complete example of that. You can read the paper if you want that example, but I think it's just takes too much time and it's not really informative. Okay, so what is our tool for actually generating these linear inductive invariants? Our tool is very much, again, the same as what we had in the previous session. It's Farkas lemma. And here's the Farkas lemma again. So basically, if you recall, the Farkas lemma was that if we assume a set of linear inequalities, so if we assume this set S, it entails another linear inequality if and only if this linear inequality can be written as a non-negative linear combination of the inequalities in S and also the trivial linear constraint that 1 is greater than or equal to 0. Or in this case, because he's working, in this paper is working with less than or equal, you would have -1 less than or equal to 0. And this is exactly what we've seen in the previous session. So you should basically be able to write C1 as a combination of A11, A21 to AM1, and then C2 as the same combination of the coefficients in the second column, and so on. Okay. Another way of looking at it is this. So if we have a bunch of linear inequalities, which we call S, we add the trivial linear inequality there, -1 is less than or equal to 0. And then we can add a bunch of coefficients, lambda 0, lambda 1 to lambda n. Okay. And what we want to see is whether we can get this condition, whether we can get this inequality as a result of these inequalities. So whether S entails psi, sorry. And the way that we do this is, again, either we find some coefficients that are multiplied by the inequalities in S and the trivial inequality, and they give us psi. Or another case is if we can get a contradiction out of S. If we can find coefficients that are multiplied by these linear inequalities in S, and when we sum them up, we get to this contradiction, 1 less than or equal to 0. If this case happens, then, well, what we know is that the conditions in S were unsatisfiable. And if S is unsatisfiable, then of course it entails everything. It vacuously entails everything. So basically, whenever we have this kind of situation and we want to see whether S entails psi, we have to solve two things. We have to see whether psi can be written as a linear combination of S and the trivial inequality, or whether we can get a contradiction as a linear combination of S and the trivial inequality, of course, with non-negative coefficients, lambda 0 to lambda. Okay, so how can this help with generating invariants? So again, what are our invariants? Our invariants are just a bunch of linear inequalities, right? So we generate a template for our invariants at every point of the program. And this is exactly like the previous session. So the only difference is that in the previous session, we were trying to find a ranking function, and a ranking function was just a function, but an invariant is a set of inequalities. So if I want one inequality at every line in my program, I create just one of these templates at every line. If I want k inequalities at every line of my program, I will create k copies of this kind of template at every line of my program. So creating the templates is just like before, okay? And then we have to write the conditions for initiation and consecution, right? Okay, so what was the condition for initiation? The condition for initiation was that if I start at line 0 of the program, if I start at the beginning of the program, and I go through some path until I get to line L, then I should satisfy eta of L. Okay, so what do I have in my table? I have the trivial inequality. I have my precondition, which was theta, and I have the path relation for the paths that I've taken. And from these, I should be able to conclude that eta holds, right? Eta was my inductive invariant. And for my inductive invariant, I actually have a template, right? Or either I have to do this, or I have to show that it's impossible to take this path. So if it's impossible to take this path, this means that if I assume theta and I assume this path, I assume the relation of this path, then I can get some sort of contradiction. And getting this contradiction is pretty much the same as saying that the path is disabled, in the meaning that this path will not be taken in any real execution of this program. Okay? So I can write the conditions for initiation basically using Farkas lemma. The only point here is that I have to do this for every path P, but because I've got rid of the cycles, this is actually a finite number of possible paths. So I'm only doing this for what we call basic paths. Or again, if our cut set is the set of all labels in the program, then we can just assume that we are doing this for every transition. Okay, so this is for initiation. And then what happens for consecution? For consecution, the thing that happens is that I'm at some line Li, and at that line, I know that eta of Li holds. So I write eta of Li as one of my assumptions. Of course, I again have the assumption that the trivial assumption that -1 is less than or equal to 0. And then I've taken some path P, so I can assume the relation of P. And what do I want to get? What do I want to be entailed from all of this? I want to make sure that when I get to the end of this path, when I get to some line Lj, I have eta of Lj, of course, the primed version at that point, because the variables are updated. So again, I have a bunch of linear inequalities, and these linear inequalities should entail another linear inequality. And again, by Farkas lemma, either I should be able to write this linear inequality as a combination of these ones, or I should be able to get a combination of these ones with non-negative coefficients, of course, that gives me a contradiction. So, as you see, everything seems to be very similar to the case with ranking functions. We just write these constraints, and then we do exactly what we did before. So we say that the coefficients on both sides of the equalities should be equal, and so on. But actually, there is something different. And let's see what's different here. The difference is that we no longer get a linear programming instance. So when we were working with ranking functions, we applied Farkas lemma, and this gave us a linear programming instance. Let's see what happens here. So in my initiation constraints, what are the things that I know, and what are the things that I'm trying to synthesize, find a value for? So I know all the coefficients here, right? Why? Because this is my precondition, which was given to me in the input. So I know all the coefficients in this part. And this is just the semantics of the program. It is the paths relationship, which I can also compute. So I know all of the coefficients here. What I don't know are the coefficients in my template, these C variables here, because I wanted to find some value. I wanted to synthesize some value for eta, and I just created a template. I created this template where I don't know the values of C, and I don't know the value of D. So I want to find all these values. And of course, I have these new variables here, the lambdas, and these are the coefficients that I'm using in my Farkas lemma. And I don't know the values of these either, right? Now, what do I want to have? I want to have lambda 0 times this inequality plus lambda 1 times this inequality, so on, to lambda m times this inequality equal this one. So when I equate the two sides, I never have a case where an unknown variable is multiplied by another unknown variable, right? So Lambda 0 is only multiplied by variables that I know the values for. Lambda 1 is only multiplied by this expression here. And I know concrete values for all of the A's and B's and so on. So when I write this, I actually get a linear programming instance. So the initiation constraints are fine. The initiation constraints only give me a linear programming instance, and this is just like the case with synthesizing ranking functions. But let's see what happens in the consecution case. So in the consecution case, again, let's look at what variables we do not know. So I'm trying to synthesize this inductive invariant eta. So I don't know the C variables here, and I don't know the D, right? But here's the problem. Up here, I have another eta at some other line, and I also don't know these C variables and this D variable. And then I have the coefficients of my Farkas lemma. And in this case, well, the first coefficient is called mu, but basically you can call it anything you want. So these are the coefficients of my Farkas lemma. And here I have the really bad case where this coefficient, which was unknown because it's a coefficient in my Farkas lemma and I want to find the value for it, is being multiplied by my template coefficients, which were also unknown because I wanted to find values for this eta. So I have these two unknown coefficients getting multiplied. And the result is that I don't get a linear programming instance, I get a quadratic programming instance. So everything is quite similar to the case of generating ranking functions, but the problem here is that because we have this kind of constraint, because we basically have two unknowns being multiplied together, we don't get linear programming, we get quadratic programming. Okay. And now what happens with this quadratic programming instance? So unlike linear programming, you cannot solve quadratic programming in polynomial time. I mean, it's really easy actually to show that quadratic programming is NP-hard. So the situation that we are in is that we can actually generate linear invariants, but we need to solve nonlinear constraints. And this is the title of this whole paper. We have to solve quadratic constraints. And solving quadratic constraints is much harder, of course. Okay. So here's an example. So this case is the case with initiation. So in initiation, you have program variables I and j, for example, here, and you have a bunch of inequalities. You have -1 less than or equal to 0, I - 2 equal to 0, and j equal to 0. And from these, you want to be able to get another inequality that is entailed by them. And this inequality is your invariant. So you don't know the coefficients in this inequality. It's like C1i plus C2j plus d less than or equal to 0. And you apply Farkas lemma, so lambda 0 times -1 plus lambda 1 times I - 2 plus lambda 2 times j should be equal to C1i plus C2j plus d. And okay, based on this, what can we do? We can basically do the same thing as before. We can say that the coefficient of I should be equal on both sides. The coefficient of j should be equal on both sides. The constant factor should be equal on both sides. So, for example, the constant factor is d here, and it's lambda 0 times -1 plus lambda 1 times -2 on the other side. So lambda 0 times -1 plus lambda 1 times -2 should be equal to d. The coefficient of I is C1 here and lambda 1 here. So lambda 1 should be equal to C1. The coefficient of j is C2 here and lambda 2 here. So lambda 2 should be equal to C2. And as you see, all of these equalities that I'm talking about are just basically linear equalities. Why? Because this was a case of initiation constraint. But now when we go here, this is a case of consecution constraint. And we have this really bad case here. And the case is that at the beginning, we can assume the invariant at the line that we started the path, but we don't know that invariant. So the invariant at the beginning is something like this, C1i plus C2j plus d less than or equal to 0. And at the end of the path, we have some other constraints, of course, but when it ends, we want to have some other inequality hold, and this inequality also has unknowns in there, because this is also one of our inductive invariants. Okay, now let's see what happens here. So I have these inequalities, and I want to show that they entail this one. So the thing that happens here is that I basically have to multiply. So mu times this plus lambda 0 times -1 plus lambda 1 times this plus lambda 2 times this expression should be equal to C1i prime plus C2j prime plus d. Okay, this is just Farkash lemma. But now let's try to equate the coefficients. So let's look at the coefficient of I, for example. The coefficient of I is 0 on this side because I prime is not the same as I, it's a different variable. So the coefficient of I is 0 here, but here the coefficient of I is mu times C1. So I'm in this really bad situation where mu times C1 should be equal to 0, and I don't know the value of mu, and I don't know the value of C1. So I have a quadratic constraint here. And the same thing, of course, happens for J because I get mu times C2. And of course, I also get mu times D. And these are all quadratic unknowns. I have two of my unknowns being multiplied together. And so basically, if you look at the paper, it gives you complete examples of, like end-to-end examples of how everything works. But the problem in the end is how you can solve these constraints. And there is no real answer to it because solving quadratic programming is NP hard. But this paper gives some heuristics, basically, that probably help in the real world. But there is no polynomial time algorithm here. Okay. So we don't have a polynomial time algorithm, but of course, if we go back to those three properties that we wanted to have, soundness, completeness, and termination, we are sure that we at least have termination, because even though quadratic programming cannot be solved in polynomial time, it can definitely be solved in finite time, right? So you will have termination. But the question is, do we have soundness and completeness? So we definitely have soundness because every invariant that we generate is an inductive invariant. Basically, every invariant that we generate satisfies initiation and consecution. Why? Because Farkash lemma was applied here, and Farkash lemma is sound and complete. So everything that we generate is actually an inductive invariant. And at the very beginning of the session, I talked about why an inductive invariant or an inductive assertion map is actually an invariant. Okay. So we have soundness. Whatever we get is definitely an invariant. But do we have completeness? Again, just as I said, everything that we generate is an inductive invariant. So we cannot have completeness for non-inductive invariants. If you have an invariant that is not inductive, then our method cannot find it. So we don't have that kind of completeness. But we have completeness for inductive invariants that are linear. So and what that means is that when we find our constraints, our quadratic constraints, any inductive invariant that is linear corresponds to one of the solutions of our system of quadratic equations. So we have this kind of completeness here. So basically putting all of these things together, we can't solve the problem in polynomial time, but in exponential time, actually we can solve the quadratic programming instance, and using that, we can have a sound and terminating algorithm that is complete for linear inductive invariance. So those two words are really the key words, linear and inductive. So we can find linear invariants that are inductive. And then this paper goes into a bunch of applications. So it talks about increment, heap sort, and so on, and shows how you can find invariants for each one of these programs using this approach. I'm not going to go through every example, but you can basically see examples of this in the paper. But probably the main important point of the paper is the last paragraph in conclusion, which is the limitation of this approach. The main limitation of this approach is that it gives you nonlinear constraints. It gives you quadratic programming instead of linear programming. And this means that it can only be applied to kind of small programs. It doesn't scale up to large programs with thousands or millions of lines. But there are also some other limitations. One important limitation is the way that we are modeling our programs. So we are modeling our programs using transition systems that were defined here. And in our transition systems, basically, we can only have one type of variable. And the type of variable that we can have are real variables. So every variable in our program can take any real value, any real number as its value. And that's kind of unrealistic because, well, in the real world, the value set of a variable cannot be infinite. Of course, it cannot be uncountable, but we are working with real variables. And at the same time, we cannot have many of the operations that one can do with integers. So for example, if you have a program that has integer division in there, or if you have a program that has overflow behavior in there, then you can't really model it as a transition system. And of course, there are many more complicated constructs in real-world programming languages that cannot be modeled directly in these transition systems. So what happens if you have, for example, an array? What happens if you have a pointer, a class, so on? And you will see that many of these results cannot really be extended to general programs. So what is the use case and utility of this kind of approach? Well, it gives us completeness. So from the theoretical point of view, it tells us what can be solved. Because we have a sound and complete algorithm, we are basically solving at least this special case entirely, right? There is nothing left to solve for linear transition systems and generating linear inductive invariance. So from a theoretical point of view, this is elegant. But also from a practical point of view, there are many programs that are actually probably modelable in terms of these transition systems. So think of any program that does scientific computations or things that have to do with physics. So consider, for example, a program that works, for example, let's say in a cyber physical system, a program that controls a medical equipment, or a program that controls a self-driving car, or a program that's, let's say, used in a Segway. These are programs that have to work with mostly physical formulas, and these physical formulas are often linear or polynomial, and then they can be usually modeled as transition systems. So this approach at least gives us a way of generating invariants for some of our real-world programs. and it also gives us completeness. Okay. So now let's talk a little bit about how we can actually extend these ideas from the linear case to the polynomial case. And the extension is basically by using something other than Farkash lemma. Again, I'm not going to go through all the details here, but I'm just going to show you the main theorem that is being used. It cannot be applied directly. It needs a lot of work in mathematical analysis, but the intuition would be there. Okay, so let's go back to our Farkash lemma for a second. So in Farkash lemma, the way that it worked was that we have a bunch of linear assumptions, linear inequalities that are our assumptions, and we want to see whether these assumptions entail some other linear inequality. Now, in the previous session, I also talked a little bit about Handelman's theorem, which handles the case where the assumptions are linear, but the consequence, the thing that we want to be entailed, is actually polynomial. Now I'm going to talk a little bit about what happens if both of them are polynomials. So what happens if my assumptions are polynomials and I want to see whether they entail another polynomial inequality or not. And this is the case where we get something called Putiner's positive Stellensatz. So positive Stellensatz is a German word. Positive means positive, of course. Stellen means places, and Satz is theorem. So it's a theorem of positive places, or a positive locus theorem. It basically gives you a characterization of where some polynomials are positive. Let's go through this. So, or to be more exact, it gives you a characterization of polynomials that are positive over a semi-algebraic set. But that's just a very fancy way of saying that it gives you exactly this, except that your assumptions are polynomial inequalities and your consequence is also a polynomial inequality. So what this theorem says is this. Suppose that you have a set V of variables. This is, so again, our program variables. And let's say that we have a bunch of polynomials over this set V. So our polynomials are G, G1, G2 to Gn, okay? So the question is, let's say that G1 to Gm are our hypotheses. We know that G1 to Gm are non-negative. When can we figure out when can we make sure that G is positive using this assumption, using the assumption that G1 to Gm are non-negative? Okay. So what Putiner's positive Stellensatz says is that given some other assumptions, if G is positive whenever all the other GIs are non-negative, then G can be written in this format. And the format is as follows. So G is basically a combination of the GIs. This is very much like Farkash lemma. So in Farkash lemma, G and GIs were linear, and we wrote G as a combination of the GIs with non-negative coefficients, right? So here G and GIs are polynomials, and we should also have non-negative coefficients. But there is a really important difference here, and the difference is that the coefficients, which are the HIs here, are no longer just constant scalars. They're actually polynomials themselves. So instead of writing G as a combination of GIs with real coefficients, I can write G as a combination of GIs, but multiply each GI but by a polynomial. What condition should this polynomial have? Well, I should be sure that this polynomial is always non-negative, because my coefficients should always be non-negative. And what polynomials are always non-negative? Well, squares are always non-negative, right? and also sums of squares are non-negative. So if I can write G in this format, such that every HI is a sum of squares, so every HI is of this format, it's like a sum of some squares, then I can be sure that whenever the GIs are non-negative, then G is also non-negative, because the sum of squares polynomials are definitely non-negative, right? So this side is obvious, but what's not obvious is the other side, and that's what actually Putinar proved, that if G is positive, whenever the GIs are non-negative, then G can definitely be written in this format. Of course, there is also some side condition. And the side condition that we need is that there should be some GI or some GK such that the set of all points where GK is greater than or equal to 0 is compact. But that's a side condition that you should be aware of when you're using this in generating, for example, polynomial invariance or polynomial ranking functions. But the main idea does not change. The main idea is that we're doing the same thing as in Farkas lemma, except that our coefficients here are not scalars. Our coefficients are sum of square polynomials. And using this technique, we can actually generate polynomial inductive invariance and also polynomial ranking functions. The main difference here is that, well, because these are no longer scalars, we also need to create some template for these. So the lambdas are also sum of square polynomials now. But at the end of the day, when we write templates for these, then we get two polynomials that are multiplied here, and we get our quadratic programming instance just as before. So even in the case where we want to generate polynomial inductive invariance, the problem is at the end reduced to quadratic programming. And it's just as hard as the linear case. And you can see more examples of this in my paper, which is this one, Polynomial Invariant Generation for Non-Deterministic Recursive Programs. I glossed over a lot of details here. So there is a lot of small nitpicky things that you should do, like with open sets, closed sets, making sure the sets that you're working with are compact and so on. But generally this works. And actually, I can show you some experimental results as well. So these are over a bunch of benchmarks. And I can show you why this whole deal with completeness is actually such an important point. So these are the programs. This is the runtime of an algorithm that uses Putinar's positive Stellensatz and this idea of quadratic programming. And these are some other methods for generating polynomial invariance. And if you look at these other methods, the main difference is that they have some heuristic or they have some different algorithm that is sound but not complete. And you usually see these kinds of trade-offs. So when you have an algorithm that is sound but not complete, it's usually much faster. For example, if you look at this column, you see that it's whenever it finds the invariant, it's much faster than a complete algorithm. But completeness is really this idea that your algorithm should not fail. Your algorithm should always find an invariant if an invariant exists. And this is why completeness is important, because over so many different benchmarks, other algorithms can just say failed, which means that I tried my best, I couldn't find an invariant. But these kinds of algorithms that are based on constraint solving, either Farkas lemma or the Putinar's positive Stellensatz, would never fail. Their runtimes might be higher, but you are sure that you can get the invariance that you want. Okay, so any questions? Okay, so that's great. If there's no questions, you can also read these papers. Yeah, and I'm done with the presentation. I think I presented everything in this paper. Let me make sure I didn't miss anything. Okay. Yeah, it talks about some heuristics and so on. Yes, that's fine. Okay, so let me stop the sharing.